Thank you. Is it supposed to be so loud? Okay. When you talk about beer, right, ingredients are an essential part, and the same is true for the universe. So that's why I think it's very appropriate that at least one of these talks about the ingredients of the universe, or what is the universe made of. And I'll hope to explain you, broadly speaking, what our current views are, and then later on you will hear about how we do this in detail. If you talk about ingredients, right, then if beer is relatively simple, and what we'll see, the universe is fairly similar to beer. If you look at beer, there's 4 ingredients: yeast, barley, hops, and water. And then you can ask, okay, which one is the most important? Does anybody have an idea? Water. That's true to some extent, but if you only drink water, you don't drink beer. Right, so that's actually, it's really a trick question. Similarly, like if you look at this one, you'd rather not drink this either, right? So, and really the upshot of this question is that really beer is a very balanced mix of all these ingredients. If you change something, so you leave out the yeast or you leave out the barley, it ain't beer, right? And Germans are very strict about it. They even have laws on this. So really it's a balanced mix of yeast, hop, barley, and water indeed. Water makes up 95% of the beer, and interestingly indeed, in that sense it's similar to the universe, because also the universe for 95% is made up of something you can't really see. People would say though that hops and yeast really give the flavor to the beer, and so there's the details that really matter, and the same is true for our universe. If we look at a universe, it really is a balanced mix. So if you want to have planets, if you want to have galaxies, you need a very balanced mix of atoms, and then there's some details, neutrinos, photons, the stuff you see, and what we'll talk about in these dark days before Christmas, 2 mystery ingredients. That will be the focus of today, because if we look at what a universe is made of and you put it in a beer glass, this is what you get. So really the stuff you probably heard most about in these talks is the froth, right? Stars. Stars make only up about 0.5% of the universe. Completely negligible for what I do for a living. The rest of the atoms in the universe, so in total together with the stars and the other details, it's 5% at best. Right? That is what people tend to talk about. In that sense, the same with beer, right? It's the yeast that gives it a distinctive flavor. So the details are important. They sort of define, in this case, the stars and the gas, define our universe, what we're made of. But 95% of the universe is dark, right? But what is exciting is that the froth we sort of understand. Those are made of atoms, whereas the bottom part, the bottom 95%, is split in 2 components. I'll explain why we think we have to split these 2. So it's not just one big pile of dark stuff, no, but there's 2 components in there. But they're exciting because we do not understand what this is. This is really unexplored territory, and basically implies there is new physics. So actually only 5% of the universe we sort of have good physical theories, the rest we're still exploring. So that's really exciting. So then you would be like, hold on a second. This is really weird. Why would we believe you? Well, Christos later on will give you a little bit more detail and hopefully will convince you that really we can study this. But just for now, there's sort of 2 important pieces of evidence. One is when we, and this is sort of historically how this dark matter has been discovered, is when we look at galaxies and look at how fast stars and gas in these galaxies is moving, we can measure this quite well. We find that if we compare that to what we expect based on the number of stars that we see, we find that they're moving way too fast. And so that would imply that these galaxies would fly apart, which we don't see. So basically that suggests there's more gravity than meets the eye. And an even better way, and that's what Christos will explain, is to look at the distortion of space-time. So Einstein tells us that when there's mass, space-time is warped, and that warping we can actually measure now with present-day techniques. And also there we see that space-time is warped more than we would naively expect. And so basically the upshot of this is that when we look at these galaxies or massive structures in the universe, we see that gravity is somehow stronger than we expect. And then there's sort of two options. One is invisible mass, so that's what we think is actually the right answer. But there could also be a problem with gravity. So some people do not really believe in dark matter. It's fine because we haven't seen it yet. And so they say, no, the problem is with gravity. So that it's really an area of active research. But this has sort of been the situation since the late 80s when people started seeing this quite in detail in galaxies. But there's another piece of evidence. If you look at the very early universe, it's very bland. You wouldn't say from this picture, but what you see there is the very early universe, because the universe has been expanding, it's getting bigger and bigger, but basically in about 13.5 billion years ago, it was much, much smaller. So the universe was smaller in the past, it was hotter, but it was also more uniform. So this is the baby picture of the universe, because at some point it got so hot that basically became a big fog and we can't see further. But that fog is nearly uniform. It's very, very bland indeed, like Budweiser. And so, but there are some small differences, and what you see here is a measurement by the Planck satellite, ESA's Planck satellite, that has measured very, very small temperature changes. So between red and blue, the temperature difference is about a 10,000th of a degree, right? So that's really, really, really little. What is remarkable that this very early universe is extremely simple. Only 6 numbers can describe it. So it's a very simple picture of the universe. And the measurements can be explained extremely well. You could have fit this with 1,000 parameters, would still be good. But we only need 6, which is somewhat, in a way, a great success, except most of these parameters we do not understand. But then, so these little variations are the seeds of the structure we see in the present-day universe. These are the beginnings of whole galaxies, whole worlds in space. And so you can see, okay, you have these small changes, gravity will pull them together, and indeed, if you look at the nearby universe, it has much more body. Right? So you see the structures that have evolved under the influence of gravity into large, like strings of galaxies, a bit of a foam-like structure. So the nearby universe is really like the foam on a beer, with large empty regions, and then walls and intersections of galaxies. However, if you sort of say, okay, I started with this very smooth early universe, and we now know that we see that's 13.6 billion years ago. If we then look at how much structure could grow in the last 13.6 billion years, you can't explain this. There's not enough visible mass in the universe to explain this. So really the body of the universe, the structure of the universe, is caused by this dark matter that's already present in this very early universe, but we can't see its signatures. It's only nowadays that we see the signature of dark matter, because that has actually been driving the formation of structure in the universe. So it's really, what you're seeing here is the result of dark matter, and these galaxies are just the froth on top. And in that sense, this dark matter is really the mechanism, the procedure that gives the universe body. And so this is where we also distinguish it from dark energy, because dark energy in a way is sort of the yin and yang, it's the opposite of dark matter. So this is why we distinguish the two. Because dark energy tries to pull things apart or push things apart. It tries to generate more and more space in the universe, whereas gravity tries to pull overdensities like galaxies and stuff together. And so they're really, in that sense, opposite forces. Gravity tries to build the universe, and dark energy tries to push things apart. And that is what you sort of see here. So gravity tries to make things come together, and dark energy tries to destroy it. And so that's the situation. We have these two components, and then you can ask, okay, what are the ingredients, right? So what do we know about them? And that is actually interesting. So dark matter comes in many flavors. So and indeed, it's been around, and people have ideas, physicists have ideas. They've made sort of different models for dark matter, because they knew from their standard model of particle physics, which they've developed in the 60s, that it needs improvements. And these improvements tend to naturally to dark matter, but different models give you different dark matters, and that's what is shown here. So we don't know really what dark matter is, but the idea is that in general it's a particle. And so we know a few things. So we do know that it's not made of atoms. So that's very clear. So this is not just atoms that we cannot see, but it's really something fundamentally new. So it's a new fundamental particle. This is why physicists are so excited about it. And we also know a little bit about its mass. It's a fairly massive, slow-moving particle. And so this is why people are trying to detect it. This is not a brewery, but this is a large detector of xenon deep underground in a mine where they're trying to detect dark matter. So they have 1 ton of xenon in there, and then they sit there and wait. And they're still waiting because they haven't seen anything yet. Well, not dark matter. They see some other stuff, but they haven't seen any dark matter. And the other option, which is quite exciting, is to make it yourself in the Large Hadron Collider. And so I have a bottle of dark matter with me, except it's empty. And so this must be a first, is we can do a bottle reading. Because this bottle is very educational, because it actually says, deep inside the Hadron Collider, physicists hurtle subatomic particles with lightning speed on a collision course with each other. They do so in pursuit of pure science, in the hope of one day being able to unlock the mystery of the elusive unseen fabric on which our universe is embroidered, dark matter. And this is written by Sean Hoyne, the brewmaster. Right? Next time read what is on the bottle, you might learn something. So that's dark matter. When we look at dark energy, the situation is really different. Lack a good explanation of the observation, and we need better data to explain the data, to explain what we see. But you saw the bottle of beer disappear because really it's different from dark matter. Dark energy is something fundamentally different. So although we don't know for sure, we think dark energy has something to do with the properties of empty space. You just take an empty piece of space, but it doesn't mean it's really nothing. It can have some energy. And so that's what we're trying to explore. But the challenge is, right, if you're trying to learn about something that we really have no good idea of what we should be doing, it's really a challenge, right? Because you're not sure in which direction to go. So that's why I really like this very famous Dutch saying, the hardest thing of all is to find a black cat in a dark room. I think that's pretty obvious, especially if there is no cat, right? And that's a little bit the challenge we're facing in this research, because we're trying to define experiments to really learn more about dark matter and dark energy, but we're never quite sure which direction we should be searching, and we are especially afraid that we're completely in the wrong track, so there is no cat. And so how do you do this? Well, this is the latest toy which I'm working on. This is a satellite which has been developed together with the European Space Agency, which hopefully will be launched in 4 years from now. Euclid, which is a telescope which will survey a very large part of the sky, about a third of the sky, with image quality comparable to the Hubble Space Telescope. So it'll be phenomenal in terms of data. And we'll plan to use it to really make an image of the dark matter distribution using the technique that Christos will tell you after the break. But it will give us a map of the dark matter distribution over cosmic time, and so we can see, right, what the balance is of dark matter and dark energy as a function of time, and that will help us to test different ideas about the nature of dark matter and dark energy. So this is really what we plan to do in the future. Right now it's a lot of technical development, making sure it'll work. And so really that we hope that once we've launched this, and after about a decade of analysis, that we can address this question, because this is really the most important question today in physics. Who ordered this? Thank you.